Good afternoon. Very happy to see all of you here. My name is Oleg Šelajev, and today we are gonna talk about GraalVM. If you have any questions or if you want to ask them later, for some reason if you don't feel comfortable asking them here in front of your peers, you can always find me online. I go by @Šelajev, and you can tweet at me, I don't know, send a pull request on the repository with a question or anything like that. I work for the Oracle Labs department on the GraalVM team. And this is a very exciting project, and I would be absolutely thrilled to share with you what I can about that. Before we start, there are a couple of important disclaimers, because this is a technical presentation, so be aware. And skipping those, let's talk about GraalVM. How many of you have heard of GraalVM? Excellent. Very, very, very good. Almost everyone. Makes me very happy. As a developer advocate, this is one of my job descriptions, to make sure that people have heard of our projects. How many of you feel that you can explain what GraalVM is? Right. This makes me very happy, because you're in the right place, right? You are here, and hopefully after this session, there will be more people confident enough to describe what GraalVM is. So, in short, in one sentence, GraalVM is a high-performance polyglot embeddable virtual machine for running programs in different languages. Right. So there are a number of languages that we support currently. It's JVM languages, JavaScript, Ruby, R, Python, some native languages. Some of those are in different levels of compatibility with the ecosystem, but the goal is to be the high-performance polyglot embeddable virtual machine. And from that, everything that GraalVM does, and all the advantages and some design choices, everything follows from that. We want to run fast. We want to run all the languages, or at least all the languages for which we have support, and we want to be able to run them in different environments. Right? Embeddable means that you can put GraalVM technology into your applications. So the goals for the project when it started, and the first commits to the technologies that became GraalVM later were done like something like 8 years ago. So it's quite a mature project at this point of time. It started with a just-in-time compiler written in Java, and the goal for GraalVM is to make programs run more efficiently. That means just pure faster. Sometimes it means that to reduce the footprint of your runtime system. Sometimes it means that we would like to remove boundaries between the polyglot systems when you switch the language. And the second promise and the second goal is to make developers more productive by providing this unified platform which you can utilize for writing programs in all the supported languages. So currently, the state of GraalVM is when we say we would like to run all the languages, it doesn't mean that we would take the random programming language and it will magically run on top of GraalVM. Of course not. There has to be some integration, but the project is built this way that this is much easier to do that than building a runtime for the language from scratch. So currently, GraalVM supports JVM languages. It supports, as I said, Ruby, R, Python, JavaScript, and the native languages. Everything that goes through LLVM can be run on GraalVM. And this technology, GraalVM stack, could be run in the JVM. So you can start your JVM and you get the JVM infrastructure, right? You can run it in hotspot, right? For example, based on the OpenJDK binaries, and you will get the hotspot runtime characteristics. You will get probably better performance because of the different JIT compiler, but you get the same garbage collection implementations, for example. You can run with G1, GC, you can give it large heaps, and so on. You can run GraalVM inside a node.js application, and then you'll get some runtime characteristics of the node. You will get the event loop in the platform, right? Because that's what Node does. You will get signal handlers that Node registers, and this would be a proper normal node, but just capable of polyglot. You can build platform dependent binaries of some of your applications. This is the standalone mode there. When we compile your application ahead of time, and then it doesn't depend on the JVM or some other environment for execution. It just links directly to the glibc and operating system libraries, or even like we can link them statically if that's possible by the operating system, and then it would be the self-contained executable without any dependencies whatsoever. And this way you can also build GraalVM, as I mentioned, into native and Java applications. Into Java applications, it's easy because everything is written in Java. The whole GraalVM project is written in Java. So how many of you mostly write Java, I mean, 3 times a week? JavaScript? Other languages? Scala? One Scala? We have great results for Scala. So you personally should check it out after with any doubts. Kotlin? I hear Kotlin is good. Some people are not convinced, but this is a different topic. We love all the languages, right? We would like to run all of them, so there are no language wars happening here. And also, so in the JVM environments, in the like Java-based applications, you can build that stack, put it in normally because it's written in Java. But also because we can compile to the native binary, we can compare to shared libraries, certain things, and then you can plug them into your native applications. How it's structured, it's a large project. It can do many things. It can be a little bit confusing about what it can do. So, but just to give you an approximate understanding how big it is, it's quite a lot. There are almost half of the project are support for the languages. So we see those in orange. And then there are the important bits in the core thing. So there is the compiler. The heart of the GraalVM project is the GraalVM compiler, which you can use both as JIT, as an ahead-of-time compiler. So it is what makes it possible to run things fast. There is some other projects and also some tooling. And in this session, I would like to mostly concentrate on the performance of the Java applications and what GraalVM can do for Java developers, since most of you are here. But we'll also touch on some polyglot, on tooling, and so on, so you get a better understanding of the whole project. So for Java programs, GraalVM can run them in 2 different scenarios. GraalVM is a JDK distribution, right? You can download the binary, you can unpack it, and then you will see that in the bin directory there is a Java utility. So you can run Java, and you can give it Java program, it will run Java. This way we can run your programs, and it will run normally with a JIT, just substituting our just-in-time compiler instead of the normal C2, which is the default most optimizing compiler used in Hotspot. And also GraalVM, we can compile the same application using the native image utility. We feed the jar files into that. The compiler analyzes them and then outputs a platform binary. You double-click on that and it runs. So this mode will have different runtime characteristics, right? Because it doesn't depend on the JVM, but it also could be very useful in some scenarios. How you get started with GraalVM? Very simple. You download GraalVM, pre-built binaries. It's also an open source project, so you can also check it out on GitHub and you can build it yourself. But you can also just take our binaries. You unpack, you put it on the path, and you can run your Java applications normally. So for Java applications, you can use GraalVM as a drop-in replacement for your current JDK distribution. How many of you run Java 8 in like production Java 8 based? Almost a half. I assume anyone runs something older than Java 8, like 7-, 7, 6, 5. No, very good, very advanced crowd. I applaud you. So the rest probably run Java 9 plus, mostly 11, right? Who runs 11? Yay, excellent. So currently, as of this moment, our binaries are Java 8 based, which means that half of you can use that as a drop-in replacement for their JDK. This month, we should be putting out the binaries based on Java 11 as well. We've been going towards supporting that for some time now, and this support now commences to the point where you can use that as well. So, and you can just drop it in, replace it, and then you can run, and you probably can see the improvement in the performance characteristics of your runtime. So your application could probably run faster. How it is happening and how it's possible, we're going to cover in the next section. So when we talk about performance, especially the peak performance, there are some misconceptions that people have about how to write code that should be fast, right? So we have a feeling what a fast code looks like, and then we can say, okay, maybe this code doesn't look like it's fast, so we should rewrite that if we're really into fast code. So, and for example, Chris Newland, the author, the performance expert, and the author of a few performance books on Java, says that to my developers, I say that if you write code that needs to be fast, it has to be simple, right? There has to be no abstractions, because abstractions bring performance overhead, right? And this is an informed opinion. This is what it was for several years, but it also one of the things that makes the developers of a compiler very sad, because it's the job for the compiler to make your code run fast, right? To optimize your code. It's not the job of the developer to limit their tool set unless you are 100% sure that you know what you're doing, as always. So the GraalVM vision is that you should be able to run your code however abstract or however readable you want that code to be, and it should run fast, and it should run as close as possible to like a very low-level detailed code. So let me show you a quick demo of this, and I'm going to show you one benchmark. Wait a second. I need to exit PowerPoint so my screen is not mirrored displays, right? Displays, and we're going to mirror the screen in just a second. Arrangement, mirror. Right, you see it now, right? You see my code, and I'm going to show this small benchmark here to you. And this was the benchmark that was inspired by, wait, make it larger. View, window. How do you do presentation mode? Enter presentation mode, right? It should be larger now. Excellent. This is a small benchmark that was inspired by another tweet exchange where somebody asked whether the GraalVM compiler is sophisticated enough to remove all the allocations and all the abstractions from a method computing hash code, right? So, and we created this small benchmark, so you can see that there are two versions that compute a hash code of a couple of fields. One is the raw. One is what you would probably write currently if you would be like, I need this code to be really, really fast. So I need to remove all the abstractions and use primitives and not call any methods and don't create any objects and never allocate anything. And it has to be small so it can be inlined properly. So you would hand optimize it, right? And normally, as a developer, what you would like to write, you would like to write an abstract version. You would like to use a library. For example, objects hash method, it takes some values and then it just delegates to the erase hashcode method, and that one iterates over the values that is provided and does exactly the same, right? It multiplies things by 31, shifts them, and then adds another number, right? So, which version do you think is faster? Who thinks that the raw version is faster? One person. Who thinks that the abstracted version is faster? Who thinks that they run in the same ballpark without noticeable overhead one on another? Interesting. This is good. This is good. You are skeptical about things, and I like that. So let's try this. Let's try this. I have this benchmark, and this benchmark is right here. This is my benchmark. Let me just remove the scores so you don't see. This is the benchmark, and I'm gonna run that. I'm gonna open the new thing so there is no tricks, right? And I would say set JDK 11. I will run this with which Java? This is my Java 11 distribution. This is fairly modern, 11.04, normal Java, right? And I will run this with Java minus jar, target, benchmarks, objects hash. This is the Java micro harness benchmark, so it will take care of warming up my code a little bit. It will take care of reducing the chance that I would do the wrong measurement, right? It will prevent the JIT compiler from cheating a little bit. At least it will try to the best, right? So it will not the compiler not allow the compiler to eliminate the code altogether, because like if you just benchmark one statement in a loop several times, then probably the compiler will be like, oh, this doesn't do any useful work, so I can just avoid doing that. So the Java micro benchmark harness is a good tool for writing your benchmarks. You still have to understand what you're doing, and you still have to interpret the numbers that it shows you, but it's a little bit easier not to write like completely wrong benchmark with it. So let's see. So we are measuring throughput, which is how many operations, how many times we can call this thing in a unit of time. So it's operations per microseconds, and you can see that the abstracted version is a little bit slower, which is like 3 times slower than the raw version of this code. Which means that if you want the code to run fast, you probably would think I would need to rewrite my code in this probably less readable or less convenient fashion. However, let's try to run the same benchmark but with a GraalVM distribution, right? Which Java? Let me try this. This is my default Java on my machine, right? I use my GraalVM distribution, but I don't want to use this particular one. Let's see what others I have. I would like to use the community edition, the open source version of the things. So let's try the GraalVM CE 19.2, right? ls current directory, and then this, and then bin, and then Java, right? Wait. Oh no, it's contents home. It's Mac, right? Contents home, bin Java, right? Minus version Java. Minus version. Right. So it's a OpenJDK based GraalVM distribution, and it's even a little based on a little bit older version of JDK, Java 8. So, but it should be reasonably similar, right? So we're gonna go to the benchmark. I'm gonna make it a little bit larger. Remember those numbers? We're gonna scroll to them. So sorry about this. I'm gonna take my Java command from here, and I will say my Java from a certain location, and minus jar benchmarks, target benchmarks, target slash benchmarks jar objects hash, right? And I'm gonna run the same thing but with the GraalVM thing, and you can already see that the abstracted version of the objects hash is not 60 operations per microsecond as is what is before, but it is similar to the numbers which we got for the raw version. And so this is not the most sophisticated benchmarking machine, right? It's a Mac. I disabled my turbo boost, so this is one thing that you always should do. You want to get replicatable, repeatable results, right? When you run benchmarks. So this is not the most sophisticated machine, so there is still some variance about like how it optimizes things just because of the other conditions, and also the 20-second benchmark is probably not the thing that will give you the most numbers. But you can see that the score for the both abstracted and the raw versions are very similar, which means that the GraalVM compiler used as a JIT looked at the code and removed the abstractions very efficiently. And we can dig deeper. We can dig up to the assembly, and it is possible that you can traverse the transformations. There is a tooling to see what the compiler exactly did at every step. But unfortunately, there is no time to do that here. But you can do that. There is tooling, and if you want, I can recommend. There was a session recently at Devoxx Belgium that was a 3-hour session, kind of like a deep dive. And there we showed a little bit more about how you can inspect what happens inside the compiler as well. Right? So if you are interested in the compiler specifically, not just using that or using the GraalVM binaries for your workloads, then you can check out that session. However, if you are just a user, if you're just using the runtime as it tends to be, you have your application and you write your code and you run it on the platform, on GraalVM, you can just assume that certain code patterns that you previously believed to be inefficient are not. So there are a number of optimizations that GraalVM does really, really well, and they're typically for the high-level abstractions. So we have great escape analysis, which means, and this is very important here in this benchmark as well. Where's my window here for the benchmark code, right? So the var args will create an array for me, right? Because that's how it does. So we can remove that array creation very efficiently, but because that doesn't need to be an array, we can remove unboxing because we pass small integers, but they used as objects to be put in their array of objects. We can remove those allocations, and we can inline very, very efficiently. So you don't have to write defensive code for certain idioms, and in general, your highly abstracted code, the code that you want to write, will run faster just because you switch to JVM with a different just-in-time compiler. And this is proven. So obviously, since we are dealing with the runtime, yes, exit presentation mode. Since we're dealing with building a runtime, we run tons of benchmarks, right? We check for the regressions, and the team is doing the job to make it fast. So we run tons of benchmarks, and we boost micro benchmarks and larger bodies of benchmarks. And then one of them that we currently think is really interesting is the Renaissance benchmark. It's a benchmark suite that uses benchmarks from other projects mostly, and it tries to benchmark more modern Java-based workloads. You can see there are some Scala benchmarks, there are some Neo4j benchmarks, there are some Akka benchmarks, as long as the others maybe more CPU heavy workloads like computing something or computing clusters, or yes, there is .e for Scala. So the reason for creating a new benchmark suite for us was because the existing ones were written a little bit ago, right? Maybe like a benchmark suite like Da Capo, probably from 10 years ago. And 10 years ago we wrote code differently. Java code that we wrote 10 years ago looks differently from Java code that we're writing now. Currently, we would like to write reactive applications. For example, we would like to use Stream API. We would like to fix the code in small methods and then make the data pass through that code rather than writing large methods that explicitly declare where to get and manipulate the data, right? So the design paradigms for writing code have shifted, but the benchmarks we usually use are still just stress testing the code how we wrote that years ago, and you can only improve what you measure. So we thought that it's very useful to have a benchmark suite that will run modern Java workloads. And you can see on the benchmarks here, this is the GraalVM Community Edition and Enterprise Edition scores normalized to the score on C2. And the benchmark suite is renaissance.dev. You can go on the website. It's open sourced. It was created in collaboration with several universities. So there are other people's input, and you can see that the GraalVM Enterprise Edition is almost universally faster by quite a large margin. It depends, because it depends on the certain code patterns and the code shape, if you will, what exactly it's doing on the workload. But the cumulative scores here, the composite score, is that the GraalVM Enterprise Edition is approximately 30% faster, and the Community Edition, the open source bits, are also faster on the cumulative score as well. So this is one benchmark that you would like to check out. And in general, we would like to encourage people to have more benchmarks and have more measurements, because we think it's very useful. Because if you just run the same workloads again and again and again and optimize for those, it's a little bit overfitting a machine learning algorithm, right? You will be very good at those particular workloads, but then you see something else, some other abstractions, and your platform will be kind of not prepared to handle them well. This is, for example, the sole Scala developer in the room can confirm that when you go from Java to writing Scala code, the Scala bytecode, the bytecode that Scala programs output, it looks a little bit different from the normal bytecode patterns that Java produces, right? And it's much harder for C2 to optimize for those. Is it correct? Yes, it is correct. I got a smile in response. I saw you checking your phone, so I checked on you. Yes, so more benchmarks are better. But you also have to understand that just running benchmarks and throwing data out there and saying, look, this is twice as fast as that, doesn't make much sense, right? You have to analyze the data, you have to interpret the data, and you have to understand what you're doing. So you have to make your own conclusions. And one thing that we can do, certainly, is if you have a workload in mind that is very dear to your heart. For example, I don't know, you run your Spark computations, or you run your Kotlin compiler, or you run something, and you know that you would like it to run fast. What you can do, you can maybe compute some data, find some, say, for example, Java flight recorder profile, record some data about the behavior of the application, and share that with us, either through the GitHub issue ticket or email us, and we can look at the compiler graphs, we can look at that particular program and figure out it's not straightforward, but we have engineers who deal with compilers like all the time, so we can see whether there are some opportunities for optimizations, right? And we can improve those particular workloads, and it would be just for you, so you can always rewrite your code to be faster, right? You can tweak the code for the compiler, and well, very many programs have done that. For example, Netty, the server, right? It's written in a way that it's very tightly optimized to how C2, the normal hotspot top-tier optimizing compiler, works, right? Because they grew together and they know what they're doing there. So they wrote code in a special manner to be very efficient on C2. The same way everyone can do that for their program, but what you can also do, you can just write your program normally, make us to take a look at that, and then we can probably improve the performance of the runtime for everyone who writes code that way, right? So not just for you, which would be very good. So keep that in mind, and we can improve performance probably fairly straightforwardly. I don't want to make that claim because I'm not the one who will be writing the optimizations, but so far the track record is that we started releasing the release candidate for the first build last spring, and then this spring we had the first product release, 19.0. Skipped 19, but immediately jumped into 19.0, and after that, currently we are at 19.3, which should be happening like very soon this month. And every time we improve performance from every release on some benchmarks, on some programs. So this is definitely possible. However, another thing that you would probably you can do with your application, and which might be very interesting in the community, is the ahead of time compilation of your programs. And this is a little bit different from optimizing the peak performance that you get with the just-in-time compiler. And this, we realize that we have to be very careful about the messaging, and we have to be very precise about what we talk about when we talk about performance, because different people understand different things. They have different things in mind when they talk about performance. Some think that performance means peak performance, peak throughput, when everything is warmed up, when you run your application for a few days, and you're ready to crunch as many numbers as possible in the unit of time, right? Some people think that performance definitely means the tail latency. How long do we serve one request? And this is very important in certain scenarios. How long could be the pause be for processing like one web request, for example, right? Or and this is important, but this is a different dimension, right? Sometimes it's directly tied to throughput, but sometimes it could be because of the garbage collection pauses or something like that. So it's a different dimension a little bit. Some people care about startup, and they come to us and say, oh, my Go application starts up faster than your Java application, and that means Go is faster. And this is a reasonable claim if you talk about startup time, but maybe if you look at the other dimensions, it maybe doesn't hold that value. But startup is a dimension that we would like to optimize across. Memory footprint, very important, because memory currently is probably the limiting factor which you get if you run your applications in the cloud, because you need to rent your compute power, and probably memory will be the thing that you pay for the most, right? So if you can limit your memory footprint, you can use different scaling methods and scale your application differently. So in general, if we talk about JIT, then the JIT mode is targeting usually the peak performance and the latency. And this is normal, and this is what the other JDK distributions, for example, OpenJDK, does normally as well, right? Because Java has been growing for 20 years with the peak throughput and the latency questions in mind. However, the AOT mode will give you different trade-off there. So ahead of time compiled application will not depend on the JVM, right? So it doesn't need to do what JVM does at startup. It doesn't need to bring up all this heavy machinery, figure out the compilation tool chains, allocate memory for the compiler, data structures, and so on. So it can start up faster, it can have a lower memory footprint, and so on. I have 50 minutes for the session, right? 40? Right, excellent. So let me show you. I thought it was 50, so we'll skip a little bit of details. We have 7 minutes. We were warming up, so to speak. Now we go into the full JIT mode. So the ahead of time compilation, as I mentioned, you feed your application to the native image utility, and what happens behind the scenes, that all the Java classes that will be ever run in your application are analyzed together, initialized, compiled, and written in the platform binary, right? So it kind of looks at your code and outputs the machine code as a JIT would do, but before the runtime. This is very important, that when you use ahead of time compilation, some things happen before you hit runtime. And from there is one very important thing that's specifically relevant for the GraalVM native images, is the closed world assumption. The analysis phase has to see all the bytecodes that will ever be executed in your program. This is paramount. This enables us to do optimizations. This enables us to cut out the parts that will never be executed, like do a little bit of tree shaking, so your binary size is in megabytes rather than the full distribution. And also that limits some usability for the dynamic parts and features in Java. You can still use them, but you need to configure them a little bit. Because when we statically analyze your code, we cannot figure out the usage of dynamic things like reflection or proxies or anything, because they are created at runtime, and we are not yet at runtime. So, native image has to be configured a little bit, and that configuration you can provide that, but also the libraries can provide that as well, and they can put that into the jar files and simplify the consumption of the libraries when you try to build a native image as an end user. One of the libraries that actually does that is Netty. So if you're building your applications based on Netty, time using the annotation processors, right? So their vision was to configure your application beforehand using annotation processor. So I have this application, I can run it. I can also compile the native image out of this. So if we look at the quotes application binary here, it's something like 60 megabytes, and it's I think like this. It's a binary that linked to the operating system, and what I can do, I can run it. It's gonna take a little bit of time on the first try, but I can run it on my machine, and it will start in milliseconds, literally, and it's ready to serve me some requests. And I will just show you that there are no tricks. It's literally what it does: quotes random, and it will spit random quotes at me. So it's a very simple application. Initially I was writing the excuse generator, but figure out the inspirational quotes are better for presentations, right? So it doesn't do much. We hit the request in response with some data and serializes some objects into JSON. Currently it doesn't hit any database or anything, but it can do. But it's a small microservice, like probably several of you are writing daily. The cool bit about this is that when I run this, and when I look at my activity manager, I can see that my quotes application takes 15 megabytes of RAM. 15 megabytes of RAM. This is an application written in Java. It runs, it serves HTTP requests, and it takes 15 megabytes of RAM. It's not even heap. It's not just heap. It's the whole process memory. You can put it in a container. You can say the container has access to 16 megabytes of RAM, and it will run in it. How amazing is that? It's non-trivial as well, but this is one of the benefits of having the native image compilation at hand. So I can show you other things. I have a few scripts here. For example, the startup test script. We will figure out the startup time now, but better. Not just what framework it tells us, but we will start this application, hit the request, and check how much time it takes to serve one request, right? Because a framework can cheat a little bit always. It can lazily load some things, and then it can say like, I'm ready. And then only when you ask to serve a request, start initializing things. I sometimes do that when people come to me with questions. Have you done that report that I asked you last week? And I was like, yeah, of course, I'm ready. And then I start working on that, right? Don't tell anyone. We are not live streaming this, right? So I can do this startup thing, startup test, and I will give it the quotes application. And you can see that it's even the CPU time. It's not even the wall clock, but the CPU consumption is absolutely negligible to get the request. I can also plot using some facility to see the CPU and the memory consumption of the application. I can plot that, so this plot test script hits 3 requests. So in the native image mode, what you can see that they can run several requests, and the CPU only spikes. The application does work only when the request hits. So there is no initialization, there is no background compilation, there is nothing like that. So it's a very efficient way to deploy applications in environments where startup and memory consumption, you can see 30 megabytes, RSS, the full resident set size, where that is important. So no more demos because we have a few slides to cover after this. Very good, very good. So back to the thing. If we talk about AAT will probably limit your memory consumption, limit your CPU usage, but also in response for configuring some dynamic features manually, right? There are options. You can trace the execution on the JVM with a special Java agent, and it will output the configuration for you, so you don't have to provide that manually, but you still have to think about that. And then it could be a very important target for your cloud deployments, and you can limit memory, and you can configure the options, and you can scale the native image applications differently, right? You can use memory much denser. There are a number of frameworks that support native images as the target. So Halidon by Oracle, Micronaut, Quarkus, and just we are working on support for Spring applications. And just recently, at DevOps, there was a session about Spring applications and native images, GraalVM native images, and there are some preliminary results. It works. I can show you a pet cleaning application using the auto configuration with annotations, the normal thing, with JPA and everything, and it runs as a native image. It's not optimized yet, so it starts like in 150 milliseconds, not 30, but it's much better than the normal way, right? And by using native image, you limit your you reduce your startup time by a lot, and it varies from framework to framework and from application to application. But the largest gains are across all of them for you by using the native image rather than running on the JVM. And the same is with memory. The same is with memory. If you want the reduction, the largest reduction comes from using the native image rather than running on the JVM. So in the future, we're gonna work and we're gonna improve the peak throughput of the native image things, because we would like it to get on par with the JIT, at least to the negligible difference, and also the latency bits, because currently the garbage collection and the native images are a little bit too throughput oriented. So it's to stop the world so it can hit pause, and it's okay and it's good when your heap is small, but if you want to run on a larger heap, that could be a challenge. But for that, you normally would use the JIT mode anyway, right? If you want to run with large heaps, longer processes, JIT is your friend. So we're gonna skip the polyglot. Our languages are good and fast, and other people are building on top of our language support. For example, Eclipse Vertex runs JavaScript, and they're one of the fastest JavaScript implementations, like for JavaScript applications, according to Tech Empower benchmarks. Our Python is fast, but not there yet for compatibility. It's the youngest. There are tooling that works for those, but one thing that I want to take one more minute maybe and talk to you is performance of your applications, because the session is about performance. So when you write your code, what you can do, you can write small methods rather than large methods. And this is important because compiler can inline small methods very easily. By writing a lot of small methods, you give compiler a lot of choices to do its job properly. The opposite, having a large method and splitting that into two different compilation units, is a little bit awkward for the JIT compiler. It probably can still do that, but it's not as perfected as inlining, right? So writing small methods, you give the compiler the chance to shine. Local allocations almost always will be eliminated. So rather than caching some data in like static variables, most probably because you're like, oh, I don't want to allocate this array, I will cache it in a static variable. That will actually be counterproductive because you allow other threads maybe to access the data, and the compiler won't be able to optimize it away. So probably you want to keep your all allocations local. On the hot pass, they will be eliminated almost always. So, and in general, do not hand optimize unless you like absolutely certain that you know what you're doing. Which means that you run benchmarks, you look at the compiler graphs, and you understand that you need help the compiler. And for the best throughput, peak performance, probably use GraalVM in the JIT mode as your runtime, and for best startup and footprint, use GraalVM native images. So you can use Java and JVM language, Node, Java native image in production. There are people who are using those. If you are working for a large corporation, you most probably want to maybe consider the enterprise version, you will get the support from Oracle. You will get additional performance fixes, higher performance, and other small things. But all in all, you should just download it, try it on your workloads, maybe use it on your applications, and give us feedback and talk to us, and join the GraalVM ecosystem. Thank you.